Now that we've seen some different ways to measure concentrations of solutions, let's talk about some colligative properties of these solutions. Well, a colligative property has to do with the amount of something, right? How much of it is present in the solution. And the idea is that the more I have, the more these properties emerge. Okay, and so there's something called Raoult's law, which is useful to describe colligative properties. Okay, Raoult's law basically says that the partial pressure of something in a solution is equal to the mole fraction of the solute multiplied by the vapor pressure of the pure solvent. Okay, and so in this equation, PA is equal to the vapor pressure of solution. XA is equal to the mole fraction of a solvent, and PA star is equal to the vapor pressure of pure solvent. Okay, and so the idea is that when I add this solute to the solvent, vapor pressure goes down. Vapor pressure decreases. And the way that I can see that is because PA has to be less than PA star, since the mole fraction of solvent has to be between 0 and 1. And so as long as I add solvent to it, the vapor pressure solution goes down. Okay. An ideal solution is one where Raoult's law is obeyed. So let's say that I have two things in there, right, an A and a B. What I can do is I can use Raoult's law for A and Raoult's law for B. Right, so for A, I would say that the vapor pressure of A is equal to PA star times XA, and the vapor pressure for B, PB, is going to equal PB star times XB. So now if I combine this with Dalton's law, right, total pressure is equal to the partial pressure of A plus the partial pressure of B. I can take this equation and insert it here. I can take this equation and insert it here. And I get that P is equal to PA star times XA times plus PB star times XB. I can do some algebra and rearrange this. And I get that P is equal to PA star minus PB star times XA plus PB star. So this graph here shows me that relationship, right? My y-axis is pressure, and my x-axis is mole fraction. So in this graph, the purple line here represents what A is doing, and you can see that this is Raoult's law for A. That is, as the mole fraction increases, vapor pressure also increases. And this green line is also Raoult's law, but now for B. Okay, so now you say, well, if it's for B, why is it going down? Well, because we're looking at A, right? So as the mole fraction of B increases, the mole fraction of A decreases. So if I read this kind of from right to left, it's increasing. Okay, so they're both Raoult's law. The total pressure is in black. So that's showing you what both of these things are doing, right? This is A and B together. So if I just took my green curve and my purple curve and I added them together, I would get the total line, which is the total pressure for the entire system for the solution. Okay, so here's an actual example of an ideal solution. Okay, on the left is something called benzene, and on the right is something called toluene or methylbenzene. And you can see that the chemical structure of benzene is pretty similar to the chemical structure of toluene, right? The only difference is this little stick here, which represents something called a methyl group, which is just a carbon and 3 hydrogens. The point is that if the solute and the solvent are similar to each other chemically, I would expect the solution to behave ideally, right? The more similar the solute and the solvent are to each other in terms of their structures, the more likely they are to interact ideally. And so you can see on this graph here, where I have my pressure on the y-axis and the mole fraction of toluene on the x-axis, each of these points fits Raoult's law pretty well, right? It's linear here for methylbenzene or toluene. It's linear here for benzene. And if I add the two curves together, I get my total curve, which is really pretty close to a straight line. So now let's talk a little bit more about what these colligative properties are. So in a colligative property, what happens is the presence of a solute can affect the properties of the solution. And there are three main colligative properties that we care about. Okay, boiling point elevation, freezing point depression, and osmotic pressure. So what I'll do is I'll show you some examples and some figures and some images, pretty pictures of these three different situations, right? Boiling point elevation, freezing point depression, and osmotic pressure. So let's revisit our phase diagram, which looks like this. So to refresh your memory on this phase diagram, pressure is on the y-axis, temperature is on the x-axis, and what I'm going to do is just write over with my pen what's going to happen for a pure solution. Okay, sorry, pure solvent. Okay, so remember there's three curves that separate the solid, the liquid, and the gas region. So what I'm going to assume is that when I have the solute present, it actually affects the properties of the solution. And instead of the solvent alone having certain intermolecular forces, I also have intermolecular forces between the solute and the solvent. And those are favorable. They want to be close together. So it's going to actually extend the region where those intermolecular forces can happen. I'm going to assume that the solute only dissolves in the liquid portion of the solvent. Okay, so what's going to happen is the liquid part of this graph is going to be extended here and here. So you'll notice that if I pick a certain pressure, like for example 1 atmosphere, and see where it crosses the x-axis for temperature, in my regular phase diagram, right, it crossed over here, now it crosses over here. There's a certain difference, which is going to be the change in the freezing point, delta TF. And similarly here, if I go right there, that would be the normal boiling point of just the pure solvent, but now I got to extend it to there. There's a certain difference here, which is the change in the boiling point. Okay, there are formulas here that say that the change in the freezing point is going to be directly proportional to the molality of the solution. Okay, delta TF equal to minus I times KF times the molality. Okay, and so I is related to something called the Van 't Hoff factor, which is just a fancy way to say how many particles do you have in the solution. Okay, and then KF and KB are constants, which will be provided for you, right? They're numbers, but just to give you an example, for water, KF is about 1.86 degrees Celsius per molal, and KB is about 0.512 degrees Celsius per molal. So the point is that as I increase the concentration or the molality of the solution, that's going to also increase this change in the freezing point and the change in the boiling point. Notice that the freezing point went down, right, got lower, and the boiling point went up, it got higher. That's why it's called freezing point depression and boiling point elevation. Okay. Last example I want to show you is something called osmotic pressure. So here's how osmotic pressure works. Let's pretend you have something called a semi-permeable membrane that separates two sides of something. And so the semipermeable membrane is right there. Okay, and so what's going to happen is on one side, I'm going to have just solvent, right? Pure solvent, maybe water molecules. On the other side, I'm going to have a solution. So this is solute and solvent. And this membrane, semipermeable membrane, separates the two sides from each other. Okay, and so the point is that this semipermeable membrane has little holes in it that allow molecules to move back and forth. But the holes are really tiny, so only small molecules can go through and not big molecules. So if the solvent is small enough, its molecules can go in either direction, right? Those are these yellow spheres. But if the solute molecules are really big, like a protein or something like that, they're too large to pass through the semipermeable membrane. Okay, so they get stuck. They can't go anywhere. They want to move, but they can't. And when they hit the membrane, they exert a pressure, which is called the osmotic pressure. And so even if the liquid levels start out the same on both sides, eventually there's going to be a difference in pressure called the osmotic pressure, because the water molecules can move, in this case, from left to right, but the big solute molecules can't go anywhere. Okay, and so this osmotic pressure, pi, is going to be directly proportional to the concentration, how much of it I have. Okay, and so the osmotic pressure, pi, is equal to the molarity, m, times the gas constant, r, times T, temperature. When you use this formula, make sure that your temperature is in Kelvin, right? Absolute temperatures.